Good day, viewers. This is 300 Plus Academy, where all we do is exams tutoring, ensuring that you ace your next exam. Okay, what we're going to be looking at today is as it relates to our chemistry practical for WAEC SSC 2024. We'll be looking at what your question is exactly going to look like in your chemistry exam. Emphasis on the word exactly what your question is going to look like. But this time around, we are looking at Redox titration, not the conventional titration between an acid and a base. But this time around, we are looking at the titration between potassium tetraoxomanganate and iron sulfate. Okay, in this case, the potassium permanganate or potassium tetraoxomanganate 7 is going to be in the burette. As you can see on your screen, it is deep purple in color, while the iron sulfate being colorless is what we are going to be pipetting as against the KMNO4 in the burette. So like you see on your screen, we have A, in this case is going to be KMNO4. It is deep purple in color, that will be in the burette. And then iron sulfate is what we're going to pipette. Depending on the kind of pipette you're using in your respective schools, it could be 20 cm cube and it could be 25 cm cube. And in this titration, we are not going to have any need for indicator, no indicator. Our indicator in this case is still going to be KMNO4 because it works as a self-indicator. What that means is that the color of KMNO4 on its own, as you're going to see during titration, has the tendency to change. So we say we don't need an indicator here because potassium permanganate, otherwise known as potassium tetraoxomanganate 7, work as a self-indicator. How does this process work is that we are going to pipette iron sulfate into a conical flask, and then we are going to have the KMNO4 in a burette, and then we titrate the KMNO4 in the burette into the conical flask. When the KMNO4 gets into the iron sulfate, the purple color of the KMNO4 is going to turn colorless. But at the end point, the KMNO4 is going to retain a faint purple color. For that reason, we are not going to need any indicator here. And at the end point, we are going to have a faint purple or pink color which appears. What is the procedure? We pipette 20 cm cube or 25 cm cube of iron sulfate. Our iron sulfate in this year's exam, in this experiment, is tagged B, and we are going to have our KMNO4 titrated. That's our A. We are going to have that in the burette. So the purple color of KMNO4 changes to colorless as it moves into the iron sulfate that we've pipetted, and at the end point, the purple color is going to be retained. That's the purple color will appear as you can see on your screen. Look at it very well. The KMNO4 we have in the burette is deep purple. The iron sulfate we have here is colorless. As we run the KMNO4 into the iron sulfate, the purple color of the KMNO4 disappears and the whole mixture we have here will be colorless. However, at the end point, a single drop, a drop or two drops of KMNO4 is enough to change the color of the whole mixture here from colorless to light pink, or you say light purple, at which point that is the end point. We then prepare our titration table talking about the Burette readings for KMNO4, which is our A. Let me indicate that KMNO4 is our A, and from there we'll be able to answer questions. You see, this particular lecture is not really about performing the experiment. Titration or titrometric analysis is what we are used to. The focus actually is what is your question going to look like? What will your calculations look like? And that is what we intend to get right for this lecture. I can tell you categorically that in your exam, the question I'm going to be putting out here, you're going to get that question at least 80% according to what we have here. So as you can see on your screen, there is a question displaying. This is the format that you're going to have your question in the exam. So, what is our question going to look like for this exam? That's exactly what you're seeing on your screen. I would implore that you take this very seriously, because I can tell you that your question is very likely going to be exactly this in your exam. If there are at all going to be any alterations to this, it's going to be very slight, and I can tell you that what you have here, you're going to have at least 80% of that replicated for your exam. As you can see on your screen, A is a solution of potassium tetrazomanganate 7, and from that we are not given any other information, so which means we don't even know the concentration of A, so which means A in this case is not a standard solution. But for B, solution B is iron 2 sulfate, and we're of course given some information about that: 1.38 gram of iron sulfate in 250 cm cube of the solution. B here is our standard solution. You are going to have a set of instruction to carry out. They say put A into the burette. Of course, you're going to be putting A into the burette using a funnel. Then you pipette 20 or 25 cm cube of B, that's your iron sulfate, into a conical flask. Then you run your KMNO for that to titrate your A from the burette into the iron sulfate you have in the conical flask, taking note of the color change from colorless to light pink or light purple. We were told to repeat the titration to obtain concordant or consistent titer value. Concordant or consistent titer value here means plus or minus 0.50 cm cube to what your instructor is going to have at your respective schools. Okay, it says tabulate your results and calculate the average volume of acid use. So what is the titration going to look like? Okay, this here is the burette reading, final burette reading, initial burette reading, and then the volume of KMNO for that's A in the burette used. The first one we're going to have is rough titration. Okay, let's say we are actually performing this. You have pipetted your FeSO for your iron sulfate, and that's in the conical flask already, and then you're ready to run in your acid. Since your KMNO4 is at the 0 mark, you say here that your initial burette reading for the rough titration is 0.00. The cm cube here already covers for the whole unit for this table. Don't forget your unit, 0.00. Okay, if we run this KMNO4 into the FeSO4 that we have here for the first titration, let us say, okay, this is stopping at 19.70. I have actually had to perform this at the at my own lab, and these are figures I have gotten, and they are very consistent, as you soon see when we get to the calculation aspect proper. Okay, let's say I started at 0.00, and at 19.70 there is a change of the old mixture here from colorless to a light purple or light pink. So it means final burette reading there is 19.70. so if I look at the volume of KMNO4 used there, that is from here to here, from here to here, from here to here. So that's 19.70 minus 0, and that way I'm still going to get 19.70. 70. So being that this is my rough titration, I am going to cross this out. Okay, I'm now going to start with my first titration. So the level of my KMNO4 here is at 19.70. I'm going to put 19.70 here, and as this is 19.70, I'm going to pipette my iron sulfate into another conical flask, and then try to run my KMNO4 into the iron sulfate. Okay, the Burette reading stopped at 39.50. So when we look at it, this here is my final Burette reading, that's 39.50. So the difference between the final Burette reading and the initial Burette reading in this case, 39.50 minus 19.70, that's going to give us 19.80, at which point I then had to fill the Burette all over again with my KMNO for. So for the second titration, I'm starting at 0.00, and when I carried out the experiment in this case, I had my final Burette reading stopping at 19.60 before a color change from colorless to a light purple occurred. So 19.60, let's say this is 90% minus 0.00, I'm still going to get 19.60. Depending on the amount of KMNO for your supply, you can stop things at the second titration, but if you have enough, of course, you can continue up until the third titration. So at 19.60, so for the third titration, I'm taking things from 19.60. This time around, it stopped at 39.20. Those are the figures I got when I performed this at the lab. But of course, students were around, very noisy, so I just had to compute the figures and use that here. So this is 39.20. 39.20, take out 19.60, I'm going to get 19.60. Aside the rough, when I look at the first, the second, and the third titration, my figures that's talking about the volume of KMNO4 used in this titration experiment all looks consistent. So that ends that, and that's as you can see in that question, it says tabulate your results. We've tabulated that. Calculate the average volume of A used. Now, volume of A used, volume of A, that's talking about our KMNO4. Volume of KMNO4 used, for you're going to be picking figures for consistent values here, and these are consistent values. Okay, they are at close range to each other. So this is 19.80 plus 19.60 plus 19.60, all divided by 3, just like we're looking for the average of this, and computing this, we're going to get 19.67 cm cube. So this here is the average volume of KMNO4 used in this titration experiment. Okay, as you see on your screen, the next thing are some set of questions which we had to deal with. Now, moving on to the real aim of this class is to look at those calculations that will come your way in the course of the exam. Okay, it says from the results we've had on from our table, VA at that point was 19.67 cm3, talking about the volume, average volume of KMNO4 use. That was 19.67. Take note of that, of course. And the information provided, as you can see on your screen, the information provided was that B is a solution of iron 2 sulfate containing 1.38 gram in 250 cm cube. So these are the information we have about B, and from this we are meant to now calculate the concentration of B in mole per dm. So the first question says concentration of B in mole per dm. So since I'm talking about B here, I'm just going to focus on B. So when we say concentration in mole per dm cube, it simply means mole of the substance divided by the volume in dm cube of the substance. In this case, we were given mass, not mole, and we know quite well that the formula for mole is mass over molar mass. So what that means here is that I'll be saying 1.38 gram divided by, at the end of the question, as you see on your screen, we're told that the relative molecular mass of iron sulfate, B is iron sulfate, is 152 gram per mole. So mass over molar mass, the molar mass here is 152. So we've dealt with the mole here, divided by the volume here is 250 cm cube, but we needed the volume to be in dm cube. How do we convert from cm cube to dm cube? We divide by 1000, so that will be 250 divided by 1000. Okay, so what we're going to have here is going to be 1.38 over 152 times 1000. This is going to turn upside down, divided by 250. And when you compute this from your calculator, what you're going to get, your CB in mole per dm cube is going to be 0.036 mole per dm cube. Yes, 0.036 mole per dm cube. This is the formula. Look at the question again. You're told to look for the concentration of B in mole per dm cube. Need I say at this point that here, when you were told that we have 1.38 gram of iron sulfate in 250 cm cube, if the question was saying we had 2.76 gram of FeSO4 in 500 cm cube, if you have these figures, you will still get exactly the same answer. You can try that out. 2.6. If the information or the instruction we were given for B was that, you see in the question display, say 1.38 gram of the salt in 250 cm cube solution. If it had been 2.76 gram of FeSO4 in 500 cm cube, we would have gotten the same answer. Okay, concentration of B in mole per dm cube, using the same formula, mole is mass over molar mass. This will still be 2.76 divided by 152, all divided by, okay, since our volume here is 500 cm cube, that will be 500 divided by 1000. That's in converting it into dm cube. That way, this is in mole and this is in dm cube. So this would have been 2.76 over 152 times 1000 over 500. And if you compute this, you will still get 0.036 mole per dm cube. That is talking about concentration of B in mole per dm cube. All right, moving on to the next question we have. We were told to calculate concentration of A in mole per dm cube. What that means is that we should look for concentration of A. That's talking about our KMNO4 in mole per dm cube. That's the question. Of course, we were not given any information about A from the question, so which means A is not a standard solution. But now that we know the concentration of B, our iron sulfate, it means that our B here is the standard solution. And of course, we all know that when it comes to titration, what we usually do is that we use a standard solution to decode or to dictate the concentration of the other solution. In this case, we'll be using this 0.036 mole per dm cube to standardize or to know the concentration of our KMNO4. So telling me to look for my Ca here, that's not a problem. Okay, what other data do I need? The volume of A used. I told you from the table before, from the titration table, the average volume of KMNO4 used is 19.67. So we have 19.67 cm cube. And our Na, if you look at this equation here, this is our A. Our Na here is 1. So my Na, number of moles of A, KMNO4 is 1. Now, talking about my B, my Cb is 0.036 mole per dm cube. And my Vb is the volume of my pipette. The volume of the pipette I used is 25 cm cube. And the number of moles of my base, number of moles of my iron sulfate, B is our iron sulfate here. The number of moles of my B is actually 5. And we know the deal that CaVa over Cb Vb equals to Na over Nb. This is we dealing with question B2. Okay, as you can see the question on your screen. So since I'm looking for Ca, I'd rather make the Ca the subject. Ca will then be equal to what? Cb, this moves to the side, Cb Vb Na divided by Va Nb. So my Ca here, what is my Cb? 0.036 times my Vb here is 25, my Na here is 1, all divided by my Va here is 19.67 times my Nb here is 5. If we compute this, we're going to get approximately 0.01 mole per dm cube. That is our Ca. That's the concentration of our potassium tetraoxo manganate. So this is how we are going to calculate that. Look at it again. You've been given the concentration of FeSO4 from the question. You were supplied information, and in the first question we were told to look for the concentration of B in mole per dm cube. We've done that. We are now using that concentration to answer B2 now. We're using 0.036 to decode the concentration of A. That's our KMNO4 in mole per dm cube. Looking at the next question, it says we should calculate the concentration of A in gram per dm cube. What we have here is concentration of A in mole per dm cube. Now we want to get the concentration in gram per dm cube. Now, take note of this formula. Concentration in gram whenever you're looking for concentration in gram per dm cube, concentration in gram per dm cube is actually concentration in mole per dm cube times molar mass. That's talking about A. In the case of KMNO4, if that be the case, we would have been given that the relative molecular mass of KMNO4 is 158 gram per mole. 158 gram per mole. So concentration of A in gram per dm cube will be the concentration in mole per dm cube is 0.01 times 158. 0.01 times 158, that is going to give us 1.58 gram per dm cube. So this here is the concentration of A in gram per dm cube, and that ends B3. Moving on to the next question, we were told to look for the number of mole of iron 2 ion in the volume of B pipetted. Okay, B4. We are looking for the number of mole of Fe2 plus in what was pipetted was 25 cm cube of FeSO4. So you're looking at number of mole, and this is 25 cm cube. Okay, let this look more like, okay, I have 25 cm cube of FeSO4 here, 25 cm cube FeSO4, and then I'm told to look for the number of moles of Fe2 plus that I have in here. How would I have been able to do that? Okay, this is very easy. You recall that the concentration of B, that's FeSO4, concentration of B is 0.036 mole per dm cube. Cb is actually 0.036 mole per dm cube. What this means is that in 1 dm cube is the same thing as 1000 cm cube. What this means is that I have 0.036 mole in 1000 cm cube. So what this means is, now I am trying to look for the number of mole that is in 25 cm cube, and here for the concentration of B, my iron sulfate, I have 0.036 mole in 1000 cm cube. Of course, there is a formula for this. N1 over V1 equals to N2 over V2. This here is an appropriate formula to use for this. So that what this means is N1 here is going to mean, okay, number of moles of iron 2 ion I am looking for that is present in 25 cm cube equals to, in this case I have 0.036 mole of iron 2 ion present in 1000 cm cube, and that's just direct. I was told to look for number of moles of iron 2 ion in 25 cm cube, when I already know, according to the concentration of B, FeSO4, that I have 0.036 mole in 1000 cm cube. So what this will mean is N number of moles of Fe2 plus is going to be 25 cm cube times 0.036 all divided by 1000 cm cube. This off. So number of moles of iron 2 ion in 25 cm cube, if you compute, is going to be 0.0009. Yes, 0.0009 mole, and I think that is justified. If in 1000 cm cube I have 0.036 mole, in a way lesser 25 cm cube here, in 25 cm cube here that I have pipetted, I should be having way less. And this question you have here is exactly what your question in your exam is going to look like. Take it very seriously, share with your friends, and of course turn on notifications so for the SALT analysis aspect, and I tell you that way you're going to ace your chemistry in this forthcoming WAEC chemistry examination. From myself and the entire team, it's bye for now.